in the beginning I did only recitations. Do you know the difference between recitations and lecturing? If you take the big classes, the freshmen, about 500, 600, 700 take that course. There's one lecturer in the main lecture hall. In general, that's lecture hall 26-100, which takes 550 seats. These students then break up in smaller groups of roughly 25 and twice a week meet with another professor who is helping them with the homework, and the homework is made up by the lecturer. The lecturer is doing all the hocus pocus in 26-100 and makes the exams, makes the homework, everything, but the recitation instructors collect the homework, discuss the homework, grade the homework, and the students can ask the recitation instructor anything they want. So when I became a professor here in 1966, the first 6 years, I think I only did recitations. And I think my first lecturing was in 1972. My lecture demonstrations and my style, which is very eccentric, and my sense of humor, and my preparation time, and my non-conventional way of presenting physics has never changed. So that was already there in 1972. The only advance I have made is that I now cover less than what I did in the old days, because I learned that what counts is not what you cover, but what counts is what you uncover. So it's way better to concentrate on a few issues, maybe one or two during a lecture, than what many professors do, cover a lot, and they're very proud on covering a lot. That's a mistake. But I learned that very early on. So, but as time went on, I started to cover less and less. First of all, there are demonstrations available at MIT. Second, I have an enormous imagination, and I came with many new demonstrations. Some were introduced maybe already in the early 70s, some were introduced later when I started to teach electricity and magnetism. Some I changed, I made them more interesting. So it's a combination of all three, and some are spectacular that I have added, but some that were there already, which are not to my credit, were also spectacular. So from day one I have always tried to choose the most non-conservative ones, change them so that they become more interesting, that students are sitting more on the edge of their seats. That's covered by no professor, that's not covered by any university as far as I know, to freshmen and sophomores. And that's a crime. Because that's what physics is all about. It's the accuracy of a measurement. When can you say that a certain theory is not valid? You can only say that if the uncertainty in your measurement excludes the prediction of the theory. If your certainty is this big and the theory says it's here, you haven't proven anything. It's consistent with the theory. If the theory predicts it's here and your measurements are here, then you can completely exclude it. So if you want to demonstrate that the period of a pendulum is independent of the angle of the pendulum, up to 10 degrees roughly, you have to do a measurement to an accuracy of about 1/100th of a second. And if you then want to demonstrate that it's also independent of the mass that is hanging on the pendulum, in which case I myself am going to hang on it, then again I do that to an accuracy of 1/100th of a second. Because suppose you make the statement that whether your angle is 5 degrees or 10 degrees, suppose you make the statement that that's the same. Well, to a millisecond accuracy it's never the same, because your reaction time is different. So what does it mean, the same? It has no meaning. What has meaning is the following. You calculate the period of that pendulum taking into account the uncertainty in the length of the string. Could be 1 centimeter uncertain, and you have to take that into account. So you come with a prediction which you write on the blackboard, and you put the uncertainty of the measurement of the string in there. So for instance, it's 4.58 seconds plus or minus 0.02. That is 200ths of a second. If now you want to prove that it's independent of angle, your measurement has to be preferably accurate to 100th of a second, because if it is accurate to 1/10 of a second, well, then every value fits, right? So you never get the same number if you do it twice, right? That would be a remarkable thing. So you make a prediction, including your reaction time, and the value that you get with your measurement has a certain uncertainty, and the predicted value has to lie in there. But whether it's here or there doesn't matter. You have then demonstrated that within the error of uncertainty, indeed the two measurements are the same. Otherwise, how can you ever prove that two things are the same? You can only prove that up to a level of uncertainty. It's possible, if you could measure it to a microsecond, that they are not the same anymore. In fact, they aren't. There is a difference between 5 degrees and 10 degrees, but it is smaller than 100th of a second. But what is lacking, 9 out of 10 physics professors, just they don't have the heart, they don't have the love, they don't radiate their enthusiasm, they are not inspiring, they're boring, they put equations on the blackboard and they don't make the people see through those equations. Those equations are threatening. Students are scared about them. And then they teach them, if you plug numbers in the equations, you get answers. But they've never fully understood the equation. So sometimes they put the wrong numbers in. Or many equations that we have can only be applied under certain conditions. If the condition isn't met, you cannot use them. And unless you make a student see through the equations, he would never even remember when they can be used and when they cannot be used.